So where we've been in terms of electricity and what you guys just took a test over, and thank you all for making an effort on that test, I greatly appreciate it, was we looked at Coulomb's law, and we showed that that was our Coulomb's constant, our charge divided by r squared. We also looked at the force was equal to QE, and that's where our electric field was going to be KQ over R squared. And we ended up looking at Ohm's law, or we haven't looked at Ohm's law, but we ended up looking at Gauss's law that talked about charges within the surface and how we could look at that. And we looked at flux, and we've been defining what an electric field looks like and all of those lovelies. But now we're going to get to what's important. So if we looked at the Earth, so I've got the Earth here, and we have a mass out here, and we know that it's attracted to the Earth, that gave us Newton's law of gravitational motion, which we saw, the universal gravitation, which we saw that looked like this, where this was the G, mass of the Earth, radius of the Earth squared, was going to give us our equivalent to our gravitational field. So we have our gravitational field here, which is very equivalent to what we saw with our electric field. All right. And one of the things that we did with that is we said, okay, if I took an object and I raised it up, right, we got this idea of potential energy. And this was mgh. So there was our potential energy, where this was our force, because this was our acceleration due to gravity. This is our force, and we have our distance. And we showed when we did this that this was a scalar product. And we didn't have to worry so much. So this is my mass, and this was my height. I'm going to do the little height thing so my picture looks good, so that you guys have that for reference. So we've got that height, and that's what we looked at in terms of mechanics. So let's look a little differently in what happens when we're in electricity. So the experiment that we set up for this week is you guys are doing a field simulation. And one of the field simulations that you want to do is that you are looking for, I have a positive bar or plate, and I have a negative bar or plate. And if I do this and I draw my electric field that's between here, we can actually create a uniform electric field. So we actually get this uniform electric field. Well, if I take a positive charge, right? I take a positive charge and I put it in here at this end, we know that that positive charge wants to be attracted to this side. That's what we did with our forces. That's what we did. But if I want to move this positive charge in this direction by a distance d, I'm actually going to have to do work. And remember that work was a force through a distance. And then we also said work was equal to a change of potential energy. So if I did this in my gravitational field, we did this work by raising the object up. We did work. And we had a change in potential energy. It's exactly what happened. We have a change in potential energy. So my work, in terms of my electrical sense, my work is going to be my force. Okay, this is my force times my change in my position. Well, that is a really good piece here that actually gives us that change. And we know that we've got that change and we can actually look at it. And that gives us this idea that we could have an electric potential. We get that electric potential. So if I do this, I take my work. So my change, my change in work is going to give me my Q. And then in here, I have my K, Q, R squared. And then I have my change in R. Guess what happens? I'm going to end up having I'm going to end up getting a K. I'm going to do this. I'm going to keep this separate. I'm going to get K, Q over R. And that's my change in potential energy. And we're going to define a electric potential as our change in potential energy divided by the charge. And this is going to be in units of joule coulombs. Or we're going to define that as a volt. And this is something that can be measured. So we can actually use a multimeter. And if you don't have a multimeter in your house, I strongly suggest that you get one because they are very, very handy devices. Even if you are just using them as a battery tester, they are extremely handy devices. But this gives us our change in potential energy. This gives us our definition of electric potential. And now the other very nice thing is my electric potential, which is now V Q over R. This is a scalar product. And I no longer have to worry about my field items. And this falls off as 1 over R. So we can actually do problems just like what we've done before. So I've got a charge here, and we're going to call this charge, we're going to give it as 5 microcoulombs. And we're going to make that a positive charge. And then I've got a negative charge here. And this one is going to be a -2 microcoulombs. These two are separated by a distance of, we're going to call this 0.3, and that's 0.3 meters. I want to know the potential at this point, which is at 0.4 meters. So I want to know the potential at 0.4 meters. Well, first thing we have to do is know this side. And this is a 3, 4, 5 triangle. So rather than go ahead and figuring it out, I'm just going to write it down, but I could have done it. I could find that R is equal to the square root of 0.3 squared plus 0.4 squared, which is going to give me the square root of 0.25, which is going to give me 0.5. So we can actually do that fairly quickly. But now to do this problem, which we had to sit there and deal with our vectors and keep track of our angles and all that lovely stuff, I can do this much simpler. But this time we have to watch the signs. So you have to watch the signs here. You have to keep track of those. So we're going to do V for the 5, which is going to be our K, Q over R, which is going to be our 8.99 times 10 to the 9th Newton meters coulombs squared, Newton meters squared, coulombs squared, times my 5 times 10 to the minus 6 coulombs divided by my 0.3, or no, this is 0.4 because it's the distance to that one. It's 0.4 meters squared. And if I do that arithmetic, oops, I knew I did something wrong. I've been squaring things in the bottom for so long, I squared it and I went, wait a second, that's not right. This gives me 112,375, which is approximately equal to 112. And I'm going to get my meter squared cancel, and I'm going to end up in units of Newton meter. Oops, that's not a square. It's a meter. So I'm going to end up in Newton meter coulombs, which is a joule coulomb, which is exactly what I want. And that's a volt. Okay. Then I'm going to do the one for the -2. I'm going to get my K, Q over R. I get my 8.99 times 10 to the 9th. And that's Newton meters squared, coulomb squared. And I get my -2 times 10 to the -6 coulombs divided by my 0.5 meters. So now I've got that cancels, that goes away. I'm going to get the same units. I'm going to get volts. But I'm going to get a negative 0.36 times 10 to the 5th. Double check my arithmetic here. Oh, So we've got that volts. Now, if I want to do this point, I'm just going to add the sum of the potentials. So now I'm going to add the sum of the potentials, and that's my 5 plus my 1 from my -2. But remember, 1 is negative, so now I'm going to get, if I do this, I'm going to get 1.12 times 10 to the 5th minus 0.36 times 10 to the 5th. That's going to equal 7.6 times 10 to the 5th. If I've done my arithmetic right. And the work to put a positive test charge, we always assume a positive test charge. Now, if I want to know the electric field at this point, well, that's cool. That's easy because now my electric field, I can just go ahead and add my vector to it and be able to work the problem that way. So that's really, really slick. Now, one of the things that you're doing in your lab is you're coming up with lines of equal potential. So let's look at that for a second. So if I have a positive charge and I have a negative charge, and you guys are going to actually do this in your simulation, if I look for lines of equal potential, I'm going to get notes that look like this. And we know that my lines of equal potential, as I drop out as 1 over R, and then I'm going to ultimately have a line of an equal potential between the two. I can actually infer my electric field because these will be perpendicular to my lines of equal potential. So this is what happens, is how you can actually draw your electric fields by looking at these lines of equal potential. So if I have a dipole, this is what we end up with, and you can actually get those. So these are my field lines. So the red is a field line, and the black is a line of equal potential. So that works out really well for us. Okay. Now, why do we worry about this? Well, because this thing right here, so we have our uniform electric field. And we're separated by a distance d. If I have this and I put a battery here, and I'm going to use a symbol for a battery. Okay, my symbol for my battery . And we know that batteries store charge. And we know from experience that we have volts. Well, if I do this, I have a device. All right, that's a device. And this device also can store charge. And we are going to define this device as a capacitor. And a capacitor has capacitance. And we're going to define this capacitance using a letter C. And that is going to be equal to the charge that's on the device divided by the voltage across it. So this is by definition what capacitance is. And this is called a parallel plate capacitor. And these are super easy to make. You can make it with a piece of aluminum foil. The big thing about a capacitor is it has to have a gap. Okay. Now, if I have air in there, that's one type of a gap. But I can put other things in here. I can put other materials. Say I can put a piece of paper. If I have a piece of paper or air or something else, it's going to change the behavior of my capacitance because this is going to have something that we call K, which we're going to call a dielectric constant. And this is a function of the material. And it turns out that the dielectric constant for air is 1. So we're going to have that as our material. So if we do this, we look at our parallel plate capacitor, basically, because that's what this is going to be. So I've got 2 plates. Okay, this one is a positive plate. This one's a negative plate. It's connected to my battery. And I want to find the capacitance. We said it's defined as the charge divided by the voltage. Well, the charge is going to equal my charge density times the area. And this is going to be charge density. Divided by the area, divided by our voltage. And our voltage, I'm going to go ahead and do this, is our electric field divided by the separation of distance d. So I'm going to give us a distance d here. So you can see exactly where that's coming from on our item. So we've got that. Now my electric field, back from Gauss's law, and that comes back from Gauss's law. So if I do all of that, I end up with my dielectric constant times the area divided by the device. And this is how I build my capacitor. So I can build any capacitor I want by looking at how it's going to be designed. Now, the one thing that I have to add in here, okay, it's because I actually told you about it already. We want to include that dielectric constant. This is for air, but I can have it as a dielectric constant. And that if I do that, I have to have my dielectric constant in the front. So this is how you calculate capacitance based on if I have a dielectric constant, if I'm using it in air, that dielectric constant is 1, and that gives me my capacitor. So for example, we want to figure out the capacitance on a parallel plate capacitor. We're given that the area is equal to 5 times 10 to the minus 3 meters squared. We've got a separation of 0.001 meters. We want to calculate the capacitance, and this is a parallel plate capacitor in air. We're just going to do K, or the E is, it's EA divided by D is going to give me my capacitance. My dielectric constant is 8.85 times 10 to the minus 12 coulombs squared Newton meters squared. So I'm going to do my 8.85 times my 10 to the minus 12. And I've got my coulombs squared, Newton meters squared. My area is 5 times 10 to the minus 3 meters squared divided by 0.001 meters. And that's going to equal 8.85 minus 12 times 5 minus 3 divided by 0.001. It's going to give me 4.425 times 10 to the minus 11. And I get one of those goes away. So I get coulombs squared Newton meters. And we're going to define that as a farad. Okay, we're going to define that as a farad. In fact, when we do this, this is also a Coulomb joule, and that is defined as our farad. Oops, no, that's not a Coulomb joule. So when something's not right, Coulomb volt. That's a Coulomb volt here. Coulomb volt, and that's a farad. So let's go through this. So if we go back to our volts, well, something didn't look right. Okay, a joule. So I've got a joule or a Coulomb. I've got a joule Coulomb is equal to a volt. And if I've got my capacitance, and that's my joule there. So if I do my Coulomb right here divided by my Newton meters, this becomes a joule or a coulomb volt, because that's a volt right here. So I want to make sure my units are making sense. And this is a farad. And 1 farad is large. One farad is really, really large because this is a nice capacitor and we're at 10 to the minus 11. So 1 farad is very, very large. So you have to worry about that. You want to make sure that you're taking care of those items there, because that makes a big thing. In fact, if I take a piece of wire across a 1 farad capacitor and discharge it right away, the wire will ultimately disintegrate. That's why we get a lot of, as you go up and you're looking at capacitors in systems, in the electric grid system, if you have a snake that comes over and crosses the capacitor and makes a connection and discharges the capacitor, there's usually not a whole lot left of the snake. So we have to worry about those things. If you are using a multimeter, you will see capacitors use this kind of a symbol, or you'll see capacitors use this symbol. Batteries use this symbol. Okay, and this is the negative side of the battery, and that's the positive side of the battery. So these are capacitors. And these are batteries. So you want to use that because we're going to draw some circuits. Okay. Now, just because of time, you've got it in Blackboard, but we are going to look at how to connect these things into a circuit. So if you think about a circuit, let's think about what happens at our house. We usually have a switch. So if I do this, I've got a switch here, and we have our wire come in, and well, like, let's say we have a little light bulb here, and this would be our circuit. Okay, so this is a light bulb, and this is a generalized circuit. Now, this is where Ben Franklin causes us all kinds of consternation, because now if I put my circuit in with our first device, this is my battery, and we're going to put it across a capacitor. So this is the same circuit that I physically drew here. We've got our battery that's connected to a plate. We got our battery that's connected to a plate, and we have our circuit. So this is positive and negative, and we're going to have the charges flow. Okay. This is the direction of charge flow. Well, that's a problem. Okay, just be aware that that's a problem, because we know that the electron is what moves. So it's actually a negative that's flowing through our circuit. So that's a problem. And we'll talk more about that when we get into current in just a little bit. But think about, for this part, we're just doing the flow of the charges. So when I put my battery in with my capacitor and I have the circuit in place, we're going to distribute charge over the capacitor. Now we can configure capacitors 2 ways. We can do it in parallel or in series. So you can do it in parallel or in series. Now, if we do it in parallel, this is how it looks. So there's my battery. Here's one capacitor. Here's another capacitor. So as the charge flows, so as my charge goes up here, when it gets to this point, it can make a choice. It can go this way or it can go that way. All right. But when I do this and I take my multimeter and I test my potential, so I test it here and I test it here and I test it here. The potential here, so we're going to call this 1. The potential here, we're going to call that 2. And the potential here from my battery, call that potential across the battery. All of these, the potential at 1 has got to equal the potential at 2, which has got to equal the potential of my battery. And I can prove that using a multimeter. All right, so we can prove that as a multimeter. But remember, my voltage is my capacitance. Well, let's do it this way. Don't want to confuse anybody by doing this. So my capacitance is defined as my charge divided by the voltage. So my voltage is going to equal my charge divided by my capacitor. All right. But if I do all of this, my voltages are all the same. Okay, my voltages are all the same. So if I'm looking at the charge on my system, the total charge is going to equal the charge on my first capacitor plus the charge on my second capacitor. Well, the charge on my system here is going to equal, if I do my charge, I'm going to do charge is equal to C times my capacitor. So this is going to be the C of C total is going to equal the voltage for my battery, which is equal to the capacitance on 1, voltage on 1, plus capacitance on 2, voltage on 2. But we know that VB equals V1 equals V2. So I get CTV is equal to C1V, which is equal to C2V. Or the capacitance total, which we're going to call the equivalent capacitance, is equal to C1 plus C2. And we could do this for multiple ones, and we can get there and go on, and we can add on. So if I'm doing in parallel, think of a ladder. If I'm in parallel, that's going to be my equivalent capacitance. Well, let's look at what happens if I'm in series. Well, here's my battery. And I'm going to come in, and now the charge has to go through one capacitor before it goes through the second capacitor before it comes to the other end. Well, it turns out that if I go here and measure my voltage, all right, that's going to tell me what I've got. And my change in voltage here is going to equal the Q over my equivalent capacitance. but my charge in the system is going to be the same. This case, I get my charge is the same. So if I'm looking at my change in voltage, that's going to be my voltage across 1 plus my voltage across 2. There's my charge over my equivalent capacitance, which is going to be the charge over my capacitance 1 plus the charge over my capacitance 2. But in this one, the charges are all the same, so that all goes away. And now I get this. And this is for series. That's for series. So let's do, we're going to take this and I'm going to draw a circuit here. We want to know what the equivalent capacitance of the system is. And this one we're going to make, we're going to do 4 microfarads, 4 microfarads. We're going to do 6 microfarads. We're going to do 3 microfarads. And we're going to do 10 microfarads. How do we do this? Well, first thing is we're going to break it up. So we're going to do this is in parallel. This one's in parallel. So we're going to do those first. Now, if I'm in parallel, the equivalent capacitance is C1 plus C2. So for that one, the equivalent capacitance is equal to 8 because I've got 4 plus 4 is equal to 8, and that's microfarads. This one, the equivalent capacitance is 6 plus 3 is going to give me 9 microfarads. And I can redraw my system. So now I've got 1, 2, 3, and this one is 8 microfarads. This one is 9 microfarads, and this one is 10 microfarads. But this one is now in series. So now I'm going to do the 1 over CEQ is equal 1 over 8 plus 1 over 9 plus 1 over 10. Oh, if I do that, now you get to play lowest common denominator or punch it into the calculator. But I'm going to do lowest common denominator. I'm going to do this is over 720. I'm going to get 90 plus 80 plus 72. I've done everything correctly. It gives me 242 divided by 720 is equal to 1 over the equivalent capacitance. And so my equivalent capacitance is going to equal 720 divided by 242. And that's going to be 2.97 microfarads. The trick is here, don't forget that this is a reciprocal, and that's usually where folks have issues. All right, that's usually where folks have issues. Now, your book does give you a problem-solving strategy. And that is, you want to do what I just did. You want to combine where you can. You want to redraw. And you'll repeat as you go through. You find the charge. When you're doing other parts of it, you can find the charge, and then you can verify by working backwards. Encourage you to do the active examples. And you have those in the practice homework. Okay, I'm going to stop there. That covers most of what you need for, oh, there's one other piece. We'll go ahead and do that because capacitors store energy, and our energy stored in a capacitor is equal to 1/2 Q times voltage, or 1/2 the capacitor times the voltage squared, or the charge squared divided by 2 times the capacitance. And that just depends on how you're given the problem. All right. That kind of goes, that's a fast through chapter 16. But it gets you kind of started. I plan on working a few more problems on Friday. I will tell you Friday's class is going to be short just because I have to travel to Alva on Friday. Questions?